Hello all, welcome. This is a session on STM32, Nucleo, FreeRTOS and SMSIS real-time operating system session. Please subscribe to our channel if you did not subscribe by clicking subscribe button. So in this session we are going with the Nucleo L476RG hardware. And let's get on to the a simple introduction to FreeRTOS. FreeRTOS is a free and open source real-time operating system that runs on many popular microcontrollers including STM32. In 2017, Amazon took control of the FreeRTOS project and now provides regular maintenance and support. If you have not set up a STM32 Cube IDE with your Nucleo board, you'll need to do so following the steps outlined in this tutorial. So what is an RTOS? So an operating system is a piece of software that manages other software and hardware in a computer system. You are probably familiar with most of the popular general purpose operating systems such as Windows, Mac OS, Linux, iOS and Android. A general purpose operating system, or shortly GPOS, is normally designed with a focus on user experience. For example, let's say we are developing an application on an operating system for a phone like Android or iOS. A user might want to stream a movie, so we can break that streaming experience into the two jobs: downloading chunks of video from the internet, that is job 1, and displaying each chunk to user, that is job 2. These jobs might be part of the same program in which they might be implemented as concurrently running threads. Okay. Chunks of video from the internet, job 1, and displaying each chunk to user, that is job 2. These jobs might be part of same program in which each they might be implemented as concurrently. If our process only has one core available, our streaming application might need to jump between job 1 and job 2 rapidly to give the user the impression that the downloading and viewing is happening at the same time. Okay. Note that I have listed a third job here, the underlying OS software. The OS is in charge of configuring out which job needs to run in order to give the user a seamless experience. This swapping of jobs is known as context switching and incurs some process overhead as the OS needs to save things like registers, memory and program counter, so that it can return to a previously running thread without losing any information. Right. A job might be a little late, a packet might be lost, or a frame might be dropped so that the video can catch up. Since the focus is on user experience in a general purpose operating system, these minor variances in job execution will likely to go unnoticed by the user, or the user might not care too much. The focus changes in most microcontroller applications. Often the focus changes in most microcontroller applications. Often meeting strict timing deadlines is critically important. Think about a motor controller or an automatic braking system in an electric vehicle. In these cases, if timing is off by even a few milliseconds, human lives could be in danger. As a result, and real-time operating systems, or RTOS, would be your best bet to manage several jobs running concurrently. So in this second example, a electric vehicle control unit, that is ECU of a electric vehicle, might be charged of controlling and assisting with braking. Job 2 monitors the driver's input and helps apply the braking and turns on the tail lights. However, let's say that our ECU gets notifications that the car sensors have detected an implementing crash. As a result, job 1 will be preempt job 2 to control the brakes. This all assumes of course, that is a vehicle equipped with automatic braking assist. Okay. Keep in mind, this is a fairly simple example. Hardware interrupt can also be used to preempt running tasks, and RTOS allows you to create software jobs instead of relying on hardware interrupts and assign them priorities. Additionally, most RTOS can act as an abstraction layer, allowing you to write code that can be easily ported to the microcontrollers. Let's see the difference between FreeRTOS and CMSIS RTOS. It is important to understand how STM32 Cube IDE has bundled FreeRTOS. While FreeRTOS is an underlying software framework that allows for switching tasks, scheduling, etc., we won't be making calls to FreeRTOS directly. ARM, Advanced Risk Management, has created the CMSIS RTOS library, which allows us to make calls to an underlying RTOS, thus improving the portability of the code among various ARM processors. That means the difference between FreeRTOS and this thing is we have a portability possible. So this, let's see the image of an CMSIS overview, library interact. So with a third-party software, if you see here, FreeRTOS is our RTOS kernel. In this depicted diagram, we will be making calls to CMSIS RTOS version 2 specifically in order to control the underlying FreeRTOS. Required hardware here is Nucleo L476 RG. I'll provide the link regarding the hardware in the description for your thing. So we have Cortex M CPU, core peripherals and other peripherals, core site, and on top of it we have CMSIS core. So here in RTOS kernel is there, there we will implement this FreeRTOS. How we do that? Enable FreeRTOS in STM32 Cube ID. Create a new C project. Okay, the image credit goes to ARM CMSIS overview, and create a new C project, your Nucleo board, and give it a name like Nucleo L476 RG FreeRTOS Blinky.in. CubeMX, go to category, middleware, FreeRTOS, under mode, change interface to just like this. Go through this. In the configuration panel, under tasks and queues, double click on the default task to make changes. Change the task name to Blink01 and change the entry function to start Blink01. Okay. Then click OK and click add to create a new task. Change the task name to Blink02. Set the party to OS priority below normal and change the entry function name to start Blink02. Note that the priority of the task 2 is below that of task 1, which means that in event of Blink01 and Blink02 trying to run concurrently, Blink01 will take priority. You will see at finally I'll add up a video how to do that. So please be patient to understand the whole stuff. So SysTick is a special timer in most ARM processor that generally is reserved for operating system purpose. By default, SysTick is in an STM32 will trigger an interrupt every 1 millisecond. If we are using the STM32 HAL, by default SysTick will be used for things like HAL underscore delay, HAL underscore get tick, As a result, the STM32 HAL framework, hardware abstraction layer framework, gives systics a very high priority. However, FreeRTOS needs systic for its scheduler, and it requires systic to be a much lower priority. Okay, so we can fix this conflict in a few ways, but the easiest to assign another unused timer as per timer based source for HL timer 6 and 7 is most STM32 microcontrollers are usually very basic, which makes them perfect as a time base for HL. So go to system core and GT just like this, and sys and under mode source to tim 6. Okay, just like this. So here I'm giving the text of it. Please go through that and save and generate the code. Write how to write a concurrent threads. Let's see at how to write the what we referred to as jobs earlier could theoretically be anything that accomplishes our desired tasks, separate programs, threads, etc. You should keep a few terminologies differences in mind when working with FreeRTOS. A task in FreeRTOS is a piece of program that can run concurrently with other pieces in the same program. It's analogous to threads. If you have done the concurrent programming, however, note that CMSIS RTOS, the abstraction layer for our RTOS, refer to these concurrent pieces of thread. As a result, you might see them used interchangeably through the program, even if they don't quite mean the same thing. Okay, so this generates a code, right? Change the main .c to the following. Copy this code. So go through this code, main.c, copy this code. I'll provide you the whole code in the listing, or please mail to us. So change the code to this, user code to end header, and then user npm and private variables. Change the code to this after it generates it, and then save it. Okay, MCO configuration. After that, user code, begin init, end init, configure the system clock, and then all the routines. Initialize the configured peripherals like a useart, begin some code there, OS kernel initialization, and RTOS mutex begin and mutex end, semaphores begin and end, and begin timers and end timers, begin RTOS queues and end RTOS queues, create the threads, definition and creation of blink01. So then give the methods just like this: const os thread iattr underscore blink attributes blink01, and priority os priority normal, stack size is 128, and same is the case with the another code also. User code, begin RTOS threads, end threads, add some threads, start scheduler, OS kernel, and then whole code. I'll provide you this in the description. Just go through this code. We'll have a quick go through of the code. Be patient, and then I'll provide you them how I do it, I'll provide you a video at the end so that you can understand what's exactly happening with this code, what are all things, what are all flexibilities we have, how to implement them. Okay, anyways, I'll provide you in the description. So in the beginning of main, you should see the threads being defined for us as set up by the CubeMX. Notice that we pass our entry function names into OS thread new function, which calls which will call all these functions as OS kernel start. Once kernel start has been called, we do not want to have any code after it in main. At this point, our thread should be running simultaneously with their own setup code and for our while loops. Therefore, there is also a background scheduler task that runs, which is in charge of switching tasks between our threads. Start blink01 and blink02 are our threads. Each has its own forever loops, and this should not run concurrently. While they can't take up the same space and time in our single core processor, the scheduler will switch them in and out to give the appearance that we are running two threads at the same time. See, there is an organization called RTIO has given a demo. Please go through that demo. It begins now, and then you can understand better what we did in this article or this session. So please kindly be patient. It would be a 7 minutes of video. So here note that instead of HAL delay we use OS delay. HAL delay in a high priority task might be the processor preventing a context switch. It also prevents a scheduler from idling, which could save on power. So we use OS delay. So OS delay tell the scheduler that it's okay to switch to a different task while we wait. We are using different delay times for blink01 and blink02 in order to have the two tasks fight over toggling the LED. Test it. Okay, build the project and start debugging session. Press the resume button to begin running the program on your Nucleo board. You should see the LD to LED on and off, but at a very duty cycle that increases on or decreases in distinct steps. This is a result of two threads with a different wait time. So let's have a look at the upcoming video, so that you will understand better. So let's play.
Specifically, we're going to use FreeRTOS as our real-time operating system kernel. With this framework, we'll want to make calls to the CMSIS RTOS API, which acts as an abstraction layer to FreeRTOS. CMSIS RTOS is maintained by ARM, and we'll be using version 2. On the side, under Reference and CMSIS RTOS API v2, you can see the functions we have available to us. We'll mostly be relying on these functions to control FreeRTOS. Notice the terminology difference. CMSIS RTOS refers to the individual jobs as threads, whereas FreeRTOS called them tasks. That can help us know if we're dealing with the CMSIS RTOS abstraction layer or the underlying FreeRTOS. In STM32 IDE, start a new STM32 project. Once again, I'll be using the Nucleo L476RG development board, so I'll give the project a name with something like FreeRTOS Blinky. We'll want to use two different tasks to control the onboard LED, which has already been configured for us on port A pin 5. In the Categories tab, go to Middleware and click on FreeRTOS. Change the interface from Disabled to CMSIS RTOS v2. In the configuration pane, we can see that most of the parameters are defined for us. These settings should be good enough for an initial test program. The important thing here is that Preemption is enabled. This allows the scheduler to stop tasks from running in order to run another task of higher priority. Go to the Tasks and Queues tab. You can see that we already have one task defined for us. Let's change its name to Blink01 and change the entry function to StartBlink01. An entry function is just a function that gets called in order to start a task or thread. Notice that the priority is set to OS normal priority. This is the default priority. We can assign tasks to be a higher or lower priority than this, but we'll leave this one at default for now. We could have just one task, but that's no different than a single forever loop. So add another task and call it Blink02. Change the entry function to StartBlink02. Click on the priority drop-down list to see the available priorities we can assign to this task. Higher priorities tell the scheduler that this task should take priority. However, we'll set this task to just below normal so that our first task takes priority. Save the file, and we get a warning about changing the time base. Systick is a special timer in most ARM Cortex-M processors that's usually reserved for calculating time slices in an RTOS. By default, Systick triggers an interrupt every 1 millisecond. Since we're using a fixed priority RTOS with preemption, tasks with higher priority will be executed first. If several tasks have the same priority, they will be executed in a round-robin type fashion. On each Systick interrupt, the scheduler will stop the current task to execute the next task with same or higher priority. The problem is that the STM32 HAL API uses the Systick timer to determine how much time has passed since restart. This is useful for things like the functions HAL delay and HAL get tick. HAL requires this timer to be at a very high priority in order to keep somewhat accurate time, at least without a real-time clock. FreeRTOS, on the other hand, requires that the time base for its scheduler is of a much lower priority. One easy fix for this is to use a different timer for HAL and leave Systick for FreeRTOS. So we go into System Core Sys and find where the STM32 HAL selects the timer for its time base. Timers 6 and 7 are often extremely basic timers with little configuration parameters, so they're best used for basic counting, just like we need for the HAL time base. So I'll go with timer 6. Save again, and CubeMX should generate code without any warnings this time. You can see that a middlewares folder and FreeRTOS files were added to our project. Open up main.c. At the top, you can see that CubeMX automatically declared the two task entry functions for us. In main, you can see that some OS kernel functions were called, which are part of CMSIS RTOS. Further down, you can see how threads are defined. We give each thread a name, priority, and stack size. This struct is then passed into the OS new thread function along with the name of our entry function to that thread, such as startblink01. Finally, OS kernel start is called, which begins running the scheduler and calls the entry functions to our threads. At this point, the RTOS has control of the system, and we should never exit from this function. As a result, you don't want to write any code past it, including in the while one loop. Scroll down to find the templates for our thread entry functions. Each thread should have a place to run some setup code and a forever loop. In the forever loop, we're simply going to toggle our LED just like we did in the first episode. For the first thread, I'm going to toggle the LED every 500 milliseconds. Notice that I'm using OS delay here, which is a CMSIS RTOS function instead of the usual HAL delay. OS delay allows the scheduler to run other tasks while we wait, whereas HAL delay might not. Ideally, we should never leave this forever loop unless the thread is terminated. However, it's usually a good idea to add a call to OS thread terminate to tell the scheduler to gracefully terminate and clean up this particular thread in case something happens, like you accidentally call break inside the forever loop. Let's repeat this same process in the startblink02 function. Note that this thread has its own separate forever loop. To us users, it will appear as if the two threads are running at the same time. If there's any question as to which should run first, Blink01 will take priority since we, set its priority higher. The difference here is that I'm going to change OS delay to 600 milliseconds. This should create an interesting effect as the two threads compete to toggle the same LED at different times. Once again, we tell the thread to terminate itself gracefully if it ever leaves the forever loop. Let's build the project and start the debugger. Inside the debugger, press the resume button. The LD2 LED on your Nucleo board should begin blinking and changing its duty cycle in distinct steps, thanks to the two threads toggling it at different times. This is just the beginning of running multiple threads on a microcontroller. How to share resources and synchronize these threads through things like queues, mutexes, and semaphores would take an entirely separate video series. But for now, have fun hacking on your STM32 with FreeRTOS, and please subscribe if you'd like to keep up with more videos like this.
So please subscribe by clicking subscribe button for more videos on this. Thank you.